Section 406.3 done states that all 120-volt single-phase 15 and 20 ampere receptacle outlets installed in bedrooms shall be protected by a ground fault circuit interrupter or GFCI. The minimum number of these outlets in each bedroom is determined by Section 210.52c. This means that the contractor installing the new outlets must ensure that they are GFCI protected. GFCI protection is designed to protect people from electric shock by detecting ground faults and interrupting the circuit. It's important to understand the scope of Section 406.3 done. It applies specifically to 120 volts, single-phase, 15 and 20 ampere receptacle outlets. GFCI protection is mandatory in bedrooms to mitigate the risk of electrical hazards. The reference to Section 210.52c highlights the importance of providing an adequate number of receptacles in bedrooms. This requirement ensures that occupants can use electrical devices safely without overloading circuits or resorting to extension cords, which can be a fire hazard. Moving on to Section 210.7 donia, which requires that receptacles installed in a wall space that is accessible behind a panel shall be provided with a faceplate or otherwise protected from contact with live parts. This is a critical safety measure. Receptacles must be properly protected to prevent accidental contact with live parts. A faceplate acts as a barrier, preventing fingers or objects from coming into contact with energized components. In situations where a faceplate cannot be used, alternative methods of protection must be employed. These methods should provide an equivalent level of safety. This requirement is intended to protect individuals who may be working or accessing areas behind panels, such as maintenance personnel or homeowners performing repairs. Now let's consider Section 250.130a. All exposed metal boxes used to enclose electrical equipment shall be grounded. Grounding metal boxes is a fundamental safety practice. Grounding provides a low impedance path for fault current to return to the source, which allows the overcurrent protective device, such as a circuit breaker or fuse, to trip and clear the fault. This prevents the metal box from becoming energized and posing a shock hazard. The term exposed refers to metal boxes that are accessible to people. Grounding is essential in these locations to minimize the risk of electrical shock. Acceptable methods for grounding metal boxes include using a grounding conductor connecting the box to a metal raceway system that is properly grounded, or using a self-grounding receptacle. Next, Section 250.146 says a grounding electrode system shall be used to ground service equipment and the electrical system. The purpose of a grounding electrode system is to provide a connection to the earth, which helps to stabilize the voltage to ground and provide a path for fault current to flow back to the source. The grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, ground plates, or metal underground water pipes, connected to the service equipment and the electrical system's grounding conductor. This system ensures that the electrical system is properly grounded, reducing the risk of electrical shock and equipment damage. The grounding electrode system is a critical component of the overall electrical safety system. It is important that the contractor has evaluated the electrical system to ensure that it can support the additional load of the new outlets. Adding new outlets increases the potential electrical load in the existing circuit. If the circuit is already close to its maximum capacity, adding more outlets could overload the circuit, leading to overheating, nuisance tripping of the circuit breaker, or even a fire. A proper load calculation should be performed to determine the existing load in the circuit and whether it can safely handle the additional load of the new outlets. If the circuit is found to be overloaded, the contractor should recommend upgrading the circuit to a higher amperage rating or installing a new circuit to serve the new outlets. The contractor should have obtained the necessary permits and inspections before performing the work. Electrical work often requires permits and inspections to ensure compliance with local codes and regulations. Obtaining permits allows the local authorities to review the proposed work and ensure that it meets safety standards. Inspections are conducted to verify that the work has been performed correctly and in accordance with the applicable codes. Failing to obtain permits and inspections can result in fines, delays, and potentially unsafe electrical installations. It is the contractor's responsibility to be aware of the local requirements and to obtain the necessary permits and inspections before starting any electrical work. Now let's elaborate further on ground fault circuit interrupters, known as GFCIs. GFCIs are crucial safety devices designed to protect individuals from electrical shock. They work by monitoring the current flowing in a circuit and quickly interrupting the power if a ground fault is detected. A ground fault occurs when electricity deviates from its intended path and flows through an unintended conductor, such as a person's body. GFCIs are designed to detect even small imbalances in current, typically around 5 mA, and trip the circuit within a fraction of a second, preventing serious injury or death. The National Electrical Code, or NEC, mandates the use of GFCIs in various locations, including bathrooms, kitchens, garages, and outdoor areas where there is a higher risk of exposure to moisture or water. In bedrooms, as highlighted in section 406.3 done, GFCI protection is specifically required for 120-volt, single-phase, 15 and 20 ampere receptacle outlets. This requirement is intended to protect occupants from electrical hazards while using appliances or devices in their bedrooms. When installing GFCI protection, it's essential to follow the manufacturer's instructions carefully and ensure that the GFCI device is properly wired and tested. Regular testing of GFCIs is also recommended to verify that they are functioning correctly and providing adequate protection. Moving on to the topic of receptacle installation according to section 210.7 Dornier. The NEC provides specific guidelines for the installation of receptacles to ensure safety and prevent electrical hazards. Receptacles must be securely mounted in approved outlet boxes and properly connected to the electrical wiring. The NEC also specifies the minimum number of receptacles required in various locations, such as walls, hallways, and countertops, to ensure convenient access to power and minimize the use of extension cords. When installing receptacles in a wall space that is accessible behind a panel, it's crucial to provide a faceplate or other means of protection to prevent accidental contact with live parts. Faceplates serve as a barrier, preventing fingers or objects from coming into contact with energized components. If a faceplate cannot be used due to space constraints or other reasons, alternative methods of protection must be employed, such as installing a recessed receptacle or using a tamper-resistant receptacle. These measures help to ensure that the receptacle is safe and prevents electrical hazards. Grounding is a critical aspect of electrical safety, and the NEC provides detailed requirements for grounding electrical systems and equipment. Grounding involves connecting electrical equipment and metal enclosures to the earth, providing a low impedance path for fault current to flow back to the source. This helps to prevent electrical shock and minimize the risk of equipment damage. Section 250.130 of the NEC requires that all exposed metal boxes used to enclose electrical equipment shall be grounded. This means that the metal box must be connected to the grounding system, either through a grounding conductor or by bonding the box to a grounded metal raceway. Grounding metal boxes helps to ensure that they remain at the same potential as the earth, preventing them from becoming energized in the event of a fault. The grounding electrode system is an essential component of the overall electrical grounding system. It provides a connection to the earth, which helps to stabilize the voltage to ground and provide a path for fault current to flow back to the source. The grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, ground plates, or metal underground water pipes connected to the service equipment and the electrical system's grounding conductor. The NEC specifies the requirements for the size, type, and installation of grounding electrodes to ensure that the grounding system is effective and provides adequate protection. The grounding electrode system is a critical safety feature that helps to minimize the risk of electrical shock and equipment damage. It is important that the grounding electrode system is properly installed and maintained to ensure that it functions correctly. Evaluating the electrical system's capacity is a crucial step before adding new outlets or increasing the electrical load on an existing circuit. Adding new outlets increases the potential electrical load in the circuit, and if the circuit is already close to its maximum capacity, it could lead to overloading, overheating, and potentially a fire. To determine whether the electrical system can support the additional load, a load calculation must be performed. A load calculation involves adding up the anticipated loads of all the devices and appliances that will be connected to the circuit. The NEC provides guidelines for calculating the loads of various types of equipment. Once the total load is calculated, it can be compared to the ampacity of the circuit breaker or fuse protecting the circuit. If the total load exceeds the ampacity of the breaker or fuse, the circuit is overloaded and must be upgraded to a higher amperage rating, or a new circuit must be installed to serve the new outlets. Obtaining permits and inspections is an essential part of any electrical work, and it's important to comply with local codes and regulations. Permits are required for most electrical work to ensure that the proposed work meets safety standards and complies with applicable codes. The permit application process typically involves submitting plans and specifications for the proposed work to the local building department for review. Once the permit is approved, the electrical work can begin. Inspections are conducted by the local building department to verify that the work has been performed correctly and in accordance with the approved plans and specifications. Inspections are typically required at various stages of the project, such as after the wiring is installed but before it is covered up, and after the project is completed. Failing to obtain permits and inspections can result in fines, delays, and potentially unsafe electrical installations. It's the contractor's responsibility to be aware of the local requirements and to obtain the necessary permits and inspections before starting any electrical work. Now let's consider an existing 2-wire receptacle outlet without a ground. This may not provide adequate protection for the new outlets. The absence of a grounding conductor in an existing 2-wire receptacle outlet raises safety concerns, especially when adding new outlets to the same circuit. In a properly grounded electrical system, a grounding conductor provides a low impedance path for fault current to flow back to the source, allowing the overcurrent protective device, such as a circuit breaker or fuse, to trip and clear the fault. This prevents the metal enclosures of electrical equipment from becoming energized and posing a shock hazard. In a 2-wire system without a grounding conductor, there is no dedicated path for fault current to flow back to the source. This means that if a fault occurs, the metal enclosures of electrical equipment could become energized, creating a shock hazard. While installing a GFCI receptacle can provide some level of protection by detecting ground faults and interrupting the circuit, it does not address the underlying issue of the absence of a grounding conductor. In some cases, it may be possible to install a grounding conductor from the receptacle outlet back to the service panel, providing a proper grounding path. However, this may not always be feasible or cost-effective. In such situations, alternative solutions may need to be considered, such as installing a new circuit with a grounding conductor or using a GFCI circuit breaker to protect the entire circuit.